Suppose you're trick-or-treating and you encounter a house with these 4 candies: Twix, peanut M&Ms, Snickers, and Reese's peanut butter cups. And let's say that the owner says you're allowed to take 2 candies. How many different choices could you make, assuming that you can't take 2 Twix or 2 Snickers? You have to take 2 different candies. Well, there's a mathematical symbol that is used to express exactly this number. It's written like this, with parentheses, and almost looks like a fraction. We read this 4 choose 2. In this case, it's the number of ways we can choose 2 candies from a collection of 4 candies. Now, if we're careful, it's not too difficult to figure out what this number is. Counting the possible pairs of candies we could select in a very organized manner, we could choose Twix and peanut M&Ms. That's one option. Or Twix and Snickers. That's 2 options. Then 3 options. 4 options, 5 options, and finally we see there are 6 possible combinations of 2 candies from the 4 on offer. And so we could write that 4 choose 2 is equal to 6. But even for small numbers, and certainly for larger numbers, these combinations become rather time-consuming to calculate, and so we're left with an obvious question. How do we calculate n choose k in general, the number of ways to choose k objects from n objects? And a second question I'm forcing upon you is, how do we find a plus b to the power of n, and why on earth does it have anything to do with n choose k? We're going to answer both of these questions today. To begin, we're going to figure out how to calculate n choose k, the number of ways to choose k objects from n objects. Let's change this situation slightly. Say a 5th candy is introduced, regular M&Ms, and again we're allowed to choose 2 of the 5 candies. How many ways could we do that? Let's see if we can figure it out just with math, and then we'll actually look at the candies and see if we can confirm our answer. Certainly, the order in which we select the candies does not matter. We're just concerned with how many different pairs we could choose. But to understand these numbers, we actually do need to understand something about order, and the number of ways that we could select these candies if order mattered. Those are called permutations, the number of ways to order a collection of objects. For example, we may ask, how many ways could we order 3 candies? If we're looking at these 3, well, certainly we have 3 choices for which candy could go first. Perhaps Twix goes first, or maybe Snickers goes first, or maybe the peanut butter cup goes first. Regardless, it's clear that if we have 3 candies, there are 3 choices for which candy goes first. If we put the peanut butter cup first, well, now we have 2 choices remaining for which candy goes second. We could put Snickers second, or we could put Twix second. Once we've chosen a candy to put second, maybe we put Twix second. Now we have only 1 choice for which candy goes third. In this case, that's Snickers. In total, we can multiply these numbers of choices together and find that there are 6 possible orderings of these 3 candies. In general, if we had n candies, the number of ways we could order them could be calculated in a similar way. We would have n candies that we could choose to go first, and once we've put 1 candy first, we have n minus 1 candies left that could go second. We would multiply those together, and then we would have n minus 2 candies that could go third, and so on, all the way down to just having a single candy and a single choice that remains. This is something we also have notation for. It's written n exclamation point. We call this a factorial, n factorial. Even though order doesn't matter in our situation where we are just selecting 2 candies from a collection of 5, these permutations and the factorial notation will actually be quite useful, partly because it's just so simple and compact. Just as another example of the factorial notation, if we were ordering 5 candies, the number of ways to do that would be 5 factorial. 5 candies that could go first, times 4 which could go second, times 3 that remain, remain that could go third, then 2 would remain that could go second, and then we'd have only a single candy left to go last. Multiplying these numbers together, we get 120. Then let's come back to our question of just selecting 2 candies from a collection of 5. These things, where order does not matter, are called combinations. We're trying to count how many combinations of 2 candies we can form from a total of 5. And of course, based on the notation that we introduced earlier, this is written like this: 5 choose 2. Now let's start to build up our calculation for this. Certainly, we know how to count the number of ways we could order 5 objects. Let's start with that. We have a collection of 5 objects, and we know the number of ways we could order 5 of those objects is 5 times 4 times 3 times 2 times 1. That's just 5 factorial. Of course, in this case, we don't actually want 5 of the objects. We have 5 to choose from, but we're only choosing 2 of them. Now, what we've written here is the number of ways to order 5 of the objects, but if we're only choosing 2 of them, well then the number of orderings for 2 objects from a collection of 5 would just be 5 times 4, because we'd have 5 objects that could go first, and for every one of those possibilities, there would be 4 objects left, which could go second. In other words, we don't actually need the 3 times 2 times 1, so let's divide it out. So we're dividing, this is why it's in the denominator, we're dividing by 3 times 2 times 1. Let's go ahead and put that in parentheses. But remember that really we're trying to count combinations, where order doesn't matter. The calculation here is telling us how many ways we can order 2 objects from a collection of 5, but we don't care about the different orders. Thus, the final thing we have to do to correct this calculation is also divide by 2 factorial. This is the number of ways to order 2 objects, and we have to divide by it in order to get rid of those orderings, so that we're just left with the number of ways to select 2 objects from a collection of 5. If our logic is right, this arithmetic is going to give us the correct answer. Noting that the 3, 2, and 1 would cancel out in the numerator and denominator, we'd be left with 5 times 4, which is 20, and 2 factorial is 2 times 1, which is 2. So this is just 20 divided by 2, which is equal to 10. So based on our logic, there should be 10 ways to choose 2 candies from this collection of 5. Let's carefully count them up and see if we're correct. We could have Snickers and Twix. That's one possibility. We could have Snickers and the peanut butter cup. That's a second possibility. Then 3, 4, 5, 6, 7, 8, 9, and finally 10 possibilities total. Our math is correct. Let's look at this formula one more time to make sure we understand the pieces, and then we'll write it out in general. In the numerator, we have the total number of ways to order the objects in our collection. Our collection has 5 objects, and so there are 5 factorial ways to order all of those objects. Now, in the denominator, notice we have 3 times 2 times 1, which is 3 factorial. 3 comes from 5 minus 2. We have 5 objects, but we're only picking 2 of them, so we need to divide by 5 minus 2 factorial. This gets rid of all those additional orderings that come from objects we're not actually selecting. Since we're not selecting the final 3 objects, those additional orderings are not relevant, and so we divide them out. Finally, for the 2 objects that we are actually selecting, their different orderings are not important either, because we don't actually care about the order, we just care about the number of combinations, and so we divide by 2 factorial to get rid of the orderings in the objects that we are choosing. And this suggests the general formula. It's top number factorial divided by bottom number factorial times top minus bottom factorial. Let's write it out. So we're answering the first question. How do we calculate n choose k, the number of ways to choose k objects from n objects? Well, it's written like this, n choose k, and it's equal to n factorial, that's the top number factorial, divided by the bottom number, k factorial, also divided by n minus k factorial. And once more, this counts up the number of ways to order all n objects. This is dividing out the number of ways to order the objects that we're not selecting, and this divides out the number of ways to order the objects that we are selecting. So we're simply left with the number of ways to choose k objects from n objects without any respect to order, because order doesn't matter. You can try the formula out yourself to confirm some pretty small, obvious examples. How many ways are there to choose 0 objects from 1 object? We say the answer to that question is 1, because the only way to do it is to just not pick anything at all. How many ways are there to choose 1 object from a collection of 1 objects? This is also just 1, which is to just choose the single object. There's only one choice. It's relevant to both of these computations that 0 factorial is defined to equal 1, so make sure you keep that in mind. A couple other small examples you could use the formula to check. How many ways are there to choose 1 object from a collection of 2? Well, you could choose the first object or the second, so there are 2 total possibilities. How many ways are there to choose 2 objects from a collection of 2? Well, the only option is to just choose the 2 objects, so there's only one way to do that. How many ways are there to choose 1 object from a collection of 3? Well, you could choose the first, second, or third object, so there are 3 choices. How many ways are there to choose 2 objects from a collection of 3? Well, if you're choosing 2 of them, you're not choosing 1 of them, and so the number of ways to choose 2 objects from a collection of 3 is just like counting the number of ways to not choose 1 from a collection of 3, so it ends up being the same number. It's 3. Now, our second question: how do we find a plus b to the power of n, and why does it have anything to do with what we just discussed, n choose k, the number of combinations of k objects from a collection of n objects? Well, to make sure you know what we're talking about, let's see an example. If you've taken Algebra 1, then you've probably seen expressions like this: x plus 1 to the power of 2, for example. This is exactly the type of expression we're talking about. It's a binomial, that is 2 terms, in this case x and 1, raised to a positive integer power, in this case 2. X plus 1 to the power of 2, you should know, is x plus 1 times x plus 1. The exponent of 2 tells us that there are 2 factors of x plus 1. And then, to do this multiplication, we just have to multiply everything in here by everything in here. That gives us x times x, which is x squared, x times 1, which is 1x, 1 times x, which is also 1x, and finally 1 times 1, which is just 1. And of course, we can simplify this by combining like terms and write it as x squared plus 2x plus 1. Now, this is probably a pretty familiar example to you, but the things in the parentheses don't have to be x and 1, and the exponent doesn't have to be 2. It could be something much larger, which is why in the question we see a plus b to the power of n. But even in this simple example, which is probably familiar to you, we can start to see why n choose k is relevant. The way that x plus 1 is multiplied by x plus 1 is by just considering all possible multiplications. We do those out and we combine like terms. For example, one possibility is that we choose x from this factor on the left and choose x from this factor on the right. Those multiply to x squared. Another possibility is that we choose 1 from this factor on the left and choose 1 from this factor on the right. Those multiply to positive 1. Another possibility is that we choose x from the factor on the left, but we choose 1 from the factor on the right. Those multiply to x. However, there are 2 ways that we could do that, because we could also choose 1 from the factor on the left and x from the factor on the right, which also produces x. In other words, there are 2 ways to choose an x from these 2 factors that both have an x. Let's look at a bigger example. Let's consider a plus b to the power of 3. We know by how exponents work that this is a plus b times a plus b times a plus b. But how do we actually do this multiplication? What does it end up equaling? Well, just like in the previous example, we have to consider all possible multiplications between these three factors. For example, we could choose a from all three factors. A times a times a gives us a cubed. Another possibility is that we choose a from the first two factors, but we choose b from the third factor, which would then give us a squared b. But that is not the only way to choose two factors of a. Instead of choosing a's from the first two factors, we could choose a from the first factor, a from the last factor, and b from the second factor, which too would give us a squared b. And there's still another way we could choose two a's. We could choose b from the first factor, but choose a's from the second two factors. That, again, would give us a squared b. And we could do a very similar thing with terms of the form b squared a. We could choose b's from the first two factors and a from the third. That would give us b squared a. However, we could also choose b from the first factor, a from the second, and b from the third. That too would give us b squared a, and then just as before, we could choose a from the first factor and b's from the second two. That gives us a third way to get b squared a. The only other possibility we haven't accounted for is choosing b from all three factors, which would thus multiply to b cubed. This gives us our final answer for the multiplication. It's a cubed plus 1, 2, 3 a squared b plus 1, 2, 3 b squared a, and then finally plus b cubed at the end. Remember when just a few minutes ago we said that there are three ways to choose two objects from a collection of three. That's exactly why we have a coefficient of 3 here with a squared b. In the term a squared b, it's like a has been chosen twice from these three factors. The number of ways to do that is 3 choose 2. The number of ways we can choose two a's from these three factors that have an a and a b, and thus when we add them all up, we have 3 total a squared b's. Viewed another way, we also saw that there were 3 ways to choose one object from a collection of 3, and we could also view a squared b under that lens. It has a single factor of b because there are 3 ways that we can choose a single b from these 3 factors. Just like with this next term, 3b squared a, there are 3 ways that we could choose a single a from these 3 factors. We could choose the a from the first factor, or the a from the second factor, or the a from the third factor. In either case, we get the 1a we choose, and then 2 factors of b, thus leaving us with the b squared. The last thing I want you to notice is that in this expansion of a plus b cubed, the powers of a are counting down, and the powers of b are counting up. First, looking at the a's, we start with a cubed, then a squared, then a to the power of 1, and then no a's at all, which is a to the power of 0. Just like with the b's, we start with no b's at all, which is b to the power of 0, then b to the power of 1, then b to the power of 2, and finally b cubed. And this leads us to one of the most well-known theorems, frankly, in all of mathematics, called the Binomial Theorem. This symbol here is an uppercase sigma, sometimes called the summation sign. It tells us to add up all terms of this form, starting at k equals 0, and then going up by 1 each time until we get to n. And this is how we expand any binomial, a plus b, to a positive integer power n. While the strange notation may be a little confusing, we've already understood all of these pieces. k starts at 0. So you notice how the b powers are going to count up, starting at 0 and then going to 1, 2, 3, and eventually stopping at n, whatever n is. Meanwhile, the powers of a begin at n, but then with each increment of k, they will reduce. It will begin with a to the n, but then it will be a to the n minus 1. And then it will be a to the n minus 2, and so on. And each term will have a coefficient, just like we saw here, which is the number of combinations of k objects from a collection of n objects. For example, this first term had a coefficient of 1 because there's only one way to select 0 objects from a collection of 3. And this last term, b cubed, also had a coefficient of 1 because there's exactly one way to select 3 objects from a collection of 3 objects. If you were asked to expand a plus b to the power of 5, you may find that a highly unpleasant task, understanding that there's a lot of multiplication to be done to figure this out. But with the binomial theorem, expanding a binomial like this to any power is pretty darn easy. To expand this, we will need to figure out the coefficients, but let me ignore the coefficients for a moment, just to make clear how simple the pattern is with the exponents. Since the power here is 5, our first term will have a to the power of 5, and b to the power of 0, which means no b at all. From then, each term will have a's power counting down and b's power counting up. Hence, the next term will have a to the power of 4 and b to the power of 1. I'm just going to leave space for the coefficients while we write these out. The next term is going to have a to the power of 3 and b to the power of 2. Again, a's exponents will count down while b's exponents count up. Then, the next term is going to have a to the power of 2 and b to the power of 3. Going to the next line to finish writing these, the next term would have a to the power of 1, b to the power of 4, and then finally we would have a to the power of 0 and b to the power of 5. Now we've expanded the binomial except for finding the coefficients, and we can find those using our combination formula with n choose k. For example, this coefficient here would be 5 choose 1, the number of ways we can choose one factor of b from a total of 5 factors. The coefficient of the next term would be 5 choose 2, the number of ways we can choose 2 factors of b from a total of 5 factors. As a result of the relationship here between combinations and the coefficients of an expanded binomial, you'll often see these things also called binomial coefficients instead of just combinations. And although we know how to calculate them, it's not necessarily the easiest, quickest thing in the world, but even for those, there is a shortcut. The shortcut is called Pascal's triangle, and it's really easy and kind of fun to write out. It starts with a 1 at the top, and then in the next row, you also have 1s. From here, the edges will always have 1s, but the other numbers will just be the sum of the 2 numbers above them. So for the third row, I would have a 1, and then add these 2 numbers, 1 plus 1, to get 2, and then again the edges have 1s. For the next row, at the edge I'd have a 1, and then 1 plus 2 is 3, 2 plus 1 is 3, at the edge we have a 1. For the next row, again at the edge we have a 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and at the edge we have a 1. What do these have to do with combinations and the coefficients of our binomial? Well, look at this row, 1, 3, 3, 1. Does that look familiar? Those are exactly the coefficients we got when we did a plus b cubed. We had 1a cubed, 3a squared b, 3b squared a, 1b cubed. The coefficients were 1, 3, 3, 1, just like you see here, 1, 3, 3, 1. So to get the coefficients of a plus b cubed, we would just need to look in row 4 of this triangle. So to get the coefficients of a plus b to the power of 5, we're going to need to look at row 6 of this triangle. Right now we have 5 rows, so we just need one more row. We're squeezing it in here, but again we have 1 at the edge, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and a 1 at the end. Notice the symmetry here with these coefficients, for example 5 and 5. This is because the number of ways you can choose one object from a collection of 5 is the same as the number of ways you can choose 4 objects from a collection of 5. They're pretty much equivalent situations. In this situation, one object is getting selected, which can happen 5 ways, and in this situation, there's one object that's not getting selected, which can also happen 5 ways. But to finish this expansion, just plug in the coefficients from the triangle. We already have a coefficient of 1, and then 5, and then 10, 10, 5, so 10, 10, 5, and the last coefficient, of course, is 1. So yeah, we started with Twix and Snickers and peanut butter cups. Maybe that was a lot more fun, but we've ended with this, and we have successfully answered our 2 questions. So good luck trick-or-treating out there. I hope your combinations are plentiful and numerous. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Climbing out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tone of words and just how I say shit. And let me speak my poetry to your face. It's not intimate if you ain't listening. Not infinite if you ain't really into it.